They provide labor services in exchange of wages. Then they receive interest income on assets, purchase goods for consumption, and they also save by accumulation of assets, right? So when we are talking about the basic Ramsey model, the basic model assumes households to be identical, right? So each household has the same preference parameter, right? So each household has the same preference parameter. So what they do is they maximize their utility function subject to a budget constraint, and the first order condition basically gives rise to this Euler equation, right? So just to recapitulate, what happens is some of the main assumptions in this model are that each households have the same preference parameters, face same wage rate because all workers are equally productive, right? Then each household begins with the same assets per person, and also there is the same rate of population growth in each household. So given these assumptions, the analysis can use the usual representative agent framework, right? So in such a framework, what happens is the equilibrium basically derives from the choices of a single household. So that's what we would be focusing on, the what choices are going to be made by a single household, right? So our representative households problem is what would give rise to the Euler equation, right? So objective function is basically utility maximization subject to budget constraint. Now now yeah these results can be generalized when various other dimensions of household heterogeneity would be introduced, but for the time being we will be focusing on households being homogeneous, right? So just think of households to be identical and all the households to be homogeneous, right? So each household, just to recapitulate, it contains one or more adult, and adults are basically working members of the current generation, so they are productive, and in making plans, they take into account the welfare and resources of their prospective descendants, right? So this is if you remember, we went through this in the last lecture. This is a model of intergenerational interaction. So the current generation basically maximizes utility and incorporates a budget constraint over an infinite horizon. So although individuals have finite lives, we would consider an immortal extended family. So this setting is basically appropriate if you assume parents to be altruistic, right? So altruistic parents basically provide transfers to their children, and the children in turn, they do the same to their children, and so on, right? So the immortal family corresponds to finite lived individuals who are connected in a way through a pattern of operative intergenerational transfers, and this is solely based on altruism. So it's not only your own interests which you would be bothered with. You should also think about your next generation's interests, and the generation after that and after that and so on. So so the individual agent whose objective function we would be looking into right now, that agent is actually altruistic, right? So the current adults expect the size of their extended family to grow at a constant rate n, because net because of several factors. Main factors are the net influences of fertility and mortality, right? So later on, what we would do is we would study how rational agents choose their fertility by weighing the costs and benefits of rearing children. But at this point in time, we would just continue to simplify by treating n, or population growth, as exogenous and constant. And we also neglect migration of people, right? So this is also something that we would incorporate later on into the basic model. So if we normalize number of adults at time 0 to unity, family size at time t, which corresponds to the adult population, is basically, it grows exponentially, right? So the population at time t is exponential nt, or e to the power e raised to nt, right? So you can call that capital LT, and the consumption is, CT, capital CT, let's say that's the total consumption at time period t, and per unit consumption would be a small ct, which is capital CT by capital LT. That's basically the consumption per adult person. So this is the household's objective function, right? So we went through this in the last class, but very quickly to recapitulate, uh, it's basically the household's objective function. It's this is the utility that the household maximizes. So overall utility u, which is integral of u small ct e to the raised to nt e to the minus of rho t. So what's the implication of this? We went through this in the last lecture. So it basically assumes that household's utility at time 0 is a weighted sum of all future flows of utility, which is small uct, right? So these are all the future flows of utility. Okay, so this function, this is often called the Felicity function. It relates the flow of utility per person to the quantity of consumption per person, which is small c. So u is it's a one-to-one function. There's a one-to-one correspondence between utility and consumption per person, right? So this Felicity function relates the flow of utility per person to the quantity of consumption per person, which is small c. So we assume that small uct, small uc, is increasing in c and it is concave, which basically means that u prime c is greater than 0, u double prime c is less than 0, just to brush up some of the assumptions that we went through. So this basically, the concavity assumption generates a desire to smooth out consumption. This is another concept also that we discussed, that agents wish to smooth out consumption based on a concave, the assumption that they have a concave utility function. Households prefer a relatively uniform pattern of consumption to one in which consumption is very low in some periods and very high in other periods. So this desire to smooth consumption derives the household's saving behavior, because they will tend to borrow when income is relatively low, and they would tend to save when income is relatively high. Okay, so also the Inada conditions would hold true, meaning that u prime c would tend to infinity as c tends to 0, and u prime c would tend to 0 as c tends to infinity, right? So this is the basic assumption. So we also, what we did was just if you look into this function, um, this it's multiplied by L, which is e raised to nt. This is the family size. E to the power nt is the family size at time t. It represents the adding up of all utilities or utils of for all family members taken together who are alive at time period t. And e to the power minus rho t, this basically involves the rate of time preference, which is rho being positive, rho being greater than 0. So positive value of rho basically means that the utils are valued less the later that they are received. The later utils would be received, the lesser their value would be. Okay, so we assume that rho is greater than n. Okay, rho is greater than n basically implies that u in this equation, it is bounded if c is constant over time. So this function is basically bounded, which follows from the assumption that rho is greater than n. Okay, so one reason for rho to be positive is that utils that would be received far in the future correspond to consumption of later generations. So suppose that starting from a point at which levels of consumption per person in each generation are the same, parents prefer a unit of their own consumption to a unit of children's consumption. This is another very sort of, it's a crucial idea. It's an idea crucial to this model, that there's a certain degree of parental quote unquote selfishness, which means that parents prefer a unit of their own consumption to a unit of their children's consumption. Although they care about their future generations, they in a way they care more about their own utility. Okay, so this certain degree of parental selfishness, it's captured by rho greater than 0, um, in this particular equation. So if we are to have a fuller specification, we would also distinguish the rate at which individuals discount their own flow of utility at different points in time. So if we do that, then basically rho equal to 0 might also apply. And the bottom line is that if we are to look at a more a complete specification, we would like to distinguish the rate at which individuals discount their own flow of utility at different points in time from the rate that applies across generations. Okay, so this equation number 1, basically assumes that only for reasons of tractability, discount rate within a person's lifetime is the same as that across generations. This is what is assumed here. I repeat that this equation is it's based on the fact that the discount rate rho within a person's lifetime is exactly the same as that across generations. Okay, so it is also plausible that parents would have diminishing marginal utility with respect to number of children. Okay, so we are going to model this effect by allowing the rate of time preference rho to increase with the population growth rate n. Okay, because we for the time being we treat n as exogenous, its dependence of rho on n would not materially change the analysis in this chapter. So we can consider this effect later on, and when we do this, that would allow for endogenous determination of population growth, right? So there would be another sort of interesting implication of that. So if rho if rho determines n, and if there's a relationship between the two, rho and n, okay, so that we would be looking into the implications of endogenous determination of population growth later on. But for the time being, let us assume that population growth is treated purely as exogenous. Okay, so households, what they do, moving on with the households problem, households uh, just show you the slides. So households basically they hold assets in the form of ownership claims on capital, and the concept of capital is going to be introduced soon, and they can they can hold assets as loans also. So negative loans in a way they represent debt, right? So we continue to assume a closed economy, so no loans can be treated treated as international loans, or like no loans can be traded internationally, and households can lend to other households, they can borrow from other households also, but the representative household will end up holding 0 net loans in equilibrium, right? So in when we are looking into the equilibrium budget constraint, we have to keep in mind that the the net holding of assets is exactly equal to 0. That would happen in equilibrium. Okay, but when we are looking to short-term fluctuations, we can have a net positive or net negative holding of assets. So because the two forms of assets, capital and loans, are assumed to be perfect substitutes as store of value, they must pay the same real rate of return, RP. So we denote the household's net assets per person as AT, where AT is measured in real terms. See here, the small AT, whenever we are doing this AT is basically it's measured in real terms, and when we are saying real terms, that means units of consumables. Okay, so AT denotes the household's net assets per person. So households are competitive in the sense that each household takes interest rate as given. Okay, so whenever you're treating the price as given, you have to keep in mind that's basically a competitive setup. Okay, so here when we are talking about price, interest rate, they're basically price of households, right? Beg your pardon, price of assets which are traded by households, right? So price of assets is interest rate, right? So demand and supply of assets are going to be determined by the interest rates and interest rates only. Here, this interest rate is treated as given, right? So households are competitive in the sense that each household takes the interest rate as given, and the wage rate also paid per unit of labor services, that is also treated as given. Okay, so we assume that each adult supplies inelastically 1 unit of labor services per unit of time. Um, right, we would also, after setting up the basic model, we are going to look into the labor leisure choice of the household, right? So in equilibrium, labor market clears, of course. Equilibrium basically means demand being, literally means demand being equal to supply. Market clearance basically means the same, that demand would be equal to supply. So when we are looking into the labor market, basically what market clearance implies is that demand for labor is equal to supply of labor, and the household obtains the desired quality of employment. Like, so whenever we are saying that labor market clears, it means that through equating demand for labor with supply of labor, the quantity of labor gets determined, and the quantity of labor that gets determined at equilibrium is the desired quantity of employment. So the model basically abstracts from involuntary unemployment, right? So there's no, in equilibrium there is no unemployment. Okay, there is no involuntary unemployment. So the labor that is determined in equilibrium is actually the desired quality of employment. Okay, so each person works 1 unit of labor services per unit of time. The wage income per adult person is also given at WT. Okay, so this is the labor income plus asset income. We went through this, and just to summarize what households do. Each person works 1 unit of labor service in one, per unit of time. Wage income is equal to WT. Total income received by aggregate households is therefore sum of labor income and asset income. This is the labor income and this is the asset income. Okay, so WT times LT, wage rate times total wage supplied and total labor supplied, and this is the asset income, is the number of total assets held, and this is the price of the interest that you would receive from holding one unit of asset. So this is the total income of the household, and households use the income that they do not consume to accumulate more assets. So savings is entirely channelized into accumulation of assets. Okay, see, this is the D assets DT. This is the assets basically represents total assets, right? Not asset per person. So this is the income that is left after consuming. This is total income minus consumption minus total consumption gives you income that is saved, and this income that is saved is entirely, it is being used to accumulate assets. D assets DT basically means the rate of change of the stock of assets. Okay, so then from here basically from the total budget constraint, we were able to obtain the budget constraint per person, right, per household. And so if you look into equation 3, that gives you an idea of the the budget constraint in per capita terms. So if each household can borrow an unlimited amount at the going interest rate, it has an incentive to pursue a form of chain later or Ponzi gain. So we would refrain from that. Household can borrow to finance current consumption and then use future borrowings to roll over the principal and pay all the interest, right? So in this case, what would basically happen is households' debt would keep on growing forever at the rate of interest RT, and effectively no principal would ever get repaid, and today's added consumption is effectively free, right? So a household that can borrow in this manner would be able to finance an arbitrarily high level of consumption in perpetuity. So we have to rule out these kind of possibilities, these kind of chain letter possibilities, and we assume, in order to do that, in order to rule out such possibilities, we assume that the credit market imposes a constraint on the amount of borrowing, and the appropriate restriction turns out to be that the present value of assets must be asymptotically non-negative, right? So that is we went through the implications of this condition, but just to sort of recapitulate this idea, this is the equation number 4 basically captures the condition that the present value of assets must be asymptotically non-negative. So this if you are to capture that condition through an equation, this would be the equation, right? So so this constraint, this is the constraint. So this condition must hold true, and if it holds true, then what it means is that in the long run, a household's debt per person, which is negative values of 80, cannot grow as fast as basically this, right? So this is the RT minus n. This is sort of the benchmark. Okay, so your debt, there's what this condition basically does is it puts a check on how fast a household's debt can grow. So you cannot keep on borrowing indefinitely, and that is ensured by this condition alone. Okay, so it cannot grow at a rate more than this. Okay, it cannot grow as far as I mean, it might grow as far as this, but it cannot exceed this RT minus n. Okay, so the level of debt cannot grow as fast as the rate of return, the interest rate. So the the interest rate on assets, your debt cannot exceed the rate of growth of interest rate, right? So this is the idea. So in order to put us in order to rule out to negate the possibility of Ponzi games, you have to ensure that the household's debt per person, mind you, cannot grow as fast as this, and the level of debt cannot grow as far as RT. That is, the level of debt cannot grow as fast as the rate of interest. Okay, so this sort of restriction rules out the type of chain letter finance that we have already gone through. We show later on how the credit market constraint expressed in this particular equation emerges naturally from the market equilibrium. Okay, so this can be reproduced solely in a competitive setup. Okay, so households optimization problem is, once again, to recapitulate, it's to maximize the utility function in equation 1 and subject to two constraints, subject to this constraint and also our main budget constraint, which is this the budget constraint in per capita terms. Okay, so we are maximizing equation 1 subject to equation 3, this one, and also we have to keep in mind that this condition would also hold true. Condition 4 would also hold true, right? So maximizing utility subject to the budget constraint in equation 3, and also taking into account the condition which ensures a no Ponzi game, which is condition represented by equation 4. Okay, all right. So also the inequality restrictions would imply that consumption is positive, so consumption per person, small ct, is greater than or equal to 0. That would also apply. Okay, Now, as small CT approaches zero, that's consumption per person approaches zero, the Inada condition basically implies that the marginal utility of consumption becomes infinite. We know this. We are already familiar with the Inada conditions. Okay, so the inequality restrictions will therefore never bind, and we can ignore the inequality restrictions for the time being, right? And just focus on the equality restrictions. Okay, so when we look into the first order, when we we have already set up the basic objective function of the household. Now, if we do the our constraint optimization, then we are doing a Hamiltonian, right? We went through this in the last lecture. And Hamiltonian, if you do it correctly, this is the first order condition that you would arrive at. Okay, after a fair bit of manipulation, this, if you do it correctly, this is what you would get. Okay, so the transversality condition is also something that you have to keep in mind. Okay, so transversality condition is it's probably I'll include that, but it's just it's the total value of assets at time t should be non-negative, right? So, and as t tends to infinity, then this value would slowly tend to zero. So that would also hold true. Okay, now if you see this is our these are the two equations that you would get by differentiating the Jacobian function with respect to the choice variables: consumption, your consumption per person, and asset per person. Okay, so now if look into this equation, equation 6 and equation 7. Just focus on equation 6 and equation 7 on the time being. Just 6 and 7 for the time being. We see these are much more tractable equations, simplistic in a way equations. So you can use these two equations to essentially derive the first order condition. So if you differentiate equation number 6 with respect to time, see, just focus on equation 6, differentiate this equation with respect to time. This is a very simple exercise. Okay, and then you can substitute for nu from this equation. You would get a value of nu after you differentiate it with respect to time, and you can substitute for nu from this equation, and for nu dot from equation 7 that you have already obtained as the second first order condition. And if you combine these two, you would get the basic condition for choosing consumption over time. And this is what you would get after some manipulation. This is what you would get. R equal to rho minus this expression u double prime c times c by u prime c. There's an implication of this just now. When you tell you the implication, times c dot by c. It's the rate of growth of consumption per person. Okay, so this is the equation that you need to understand now. Just forget everything else, just focus on equation number 9. Okay, so what this equation says is that the households choose consumption, right? Consumption is very much a choice variable. So households choose consumption so as to equate the rate of return R to the rate of time preference rho. Okay, rate of return should be equal to rate of time preference plus this thing. So what is this? This is the decrease of the marginal utility of consumption, which is u prime, due to the growing of per capita consumption C, right? So this is a concave function. So whenever per capita consumption grows, there would be a decrease of marginal utility of consumption, right? So this is this is the literal interpretation of this equation, right? So literal interpretation is households are going to choose consumption in a way that the rate of return should be equal to the rate of time preference, which is rho, plus the rate of decrease of marginal utility of consumption, which is u prime, And why is U prime going to decrease? Because of growth of per capita or per person consumption. Okay, so choice variable C, is going to be determined in a way so that R is equal to rate of time preference plus rate of decrease of marginal utility of consumption due to growing of per capita consumption. Now, what is the economic implication of this? So when we are talking about the interest rate, see on the left hand side of equation number 9, we have the interest rate, right? It's the rate of interest. So this interest rate is, what is it representing? It is representing the rate of return to saving, right? So the far right hand side of the equation can be viewed as the rate of return to consumption. Okay, so the this is the right hand side, this is the far right hand side. So the far right hand side is actually the rate of return to consumption. And why is it important? Because agents prefer to consume today rather than tomorrow. Right? I repeat, agents prefer to consume today rather than tomorrow, and this happens for two reasons. Firstly, because households discount future utility at a rate rho, right? So that is the sole significance of the rate of time preference rho. We have a rate of time preference. This in itself implies that households are impatient. Households view the present more than the future. That is, households attach more value to the present as compared to the future. Okay, so agents would prefer to consume today rather than tomorrow, because households discount future utility at the rate rho, and this rate is part of the rate of return to consumption today. Secondly, if C dot by C is positive, right? That is, if C, that is consumption per person, is low today relative to tomorrow, then you have the rate of growth of consumption per person to be positive. So since agents like to smooth consumption over time, because U double prime C is less than 0, they would like to even out the flow by bringing some future consumption forward to the present, right? Because consumption it's always preferable to consume at present rather than in the future, right? So since agents would like to smooth out consumption over time, because of our assumption of concavity, because of the assumption that U double prime C is less than 0, agents would like to even out or smooth out the flow by bringing some future consumption forward to the current time period or to the present. So the second term on the far right, actually this term actually picks up this effect. So if agents are optimizing, then this Euler equation, this equation number 9 is actually called your Euler equation. This Euler equation says that agents have equated the two rates of return and are therefore indifferent at the margin between consuming and saving. Okay. So this is important for us to understand. So, another way of viewing this Euler equation is that the households would select a flat consumption profile any day to a very bumpy or irregular consumption profile or consumption pattern. So a very smooth or very flat consumption profile basically means that C dot C is close to 0. C dot by C is close to 0, or C dot by C is almost equal to 0, meaning that this is not growing over time. This is remaining, consumption per person is remaining flat, remaining constant more or less. And that would close to 0 or almost equal to 0 if R is almost equal to rho. If the rate of interest is almost equal to the rate of time preference. So households would be willing to depart from this very flat pattern and in a way, sacrifice some consumption today for more consumption tomorrow. That is, they're going to tolerate, some positive C dot by C or some growth in small c, only if they are compensated, right? And how are they going to be compensated? They would be compensated by an interest rate R that is sufficiently above rho. So R has to be greater than rho if households tolerate some positive growth in consumption, right? So if households are to tolerate C dot by C greater than 0 rather than C dot by C being equal to 0, because keep in mind households would any day prefer C dot by C to be equal to 0, right? So if they are to tolerate C dot by C to be greater than 0, that would be possible only if they are going to be compensated by an interest rate R that is considerably higher than the rate of time preference rho. Okay, so the term, this term, u double prime c times c divided by u prime c times c dot by c, this entire term taken together, or if you look into the expression on the right hand side, the entire expression barring rho, that term, this term within square brackets and first brackets, uh, what it means is, this basically gives the required amount of compensation. So note that the term in brackets is the magnitude of the elasticity of u prime c with respect to c. This in itself is the elasticity of u prime c with respect to c. So the elasticity is basically a measure of concavity of the utility function uc, and what it does is it basically determines the amount by which your rate of interest must exceed rho. Okay, so if the elasticity is larger in magnitude, then the required premium of interest rate over rho is greater for a given value of C dot by C, or for a given value of growth in consumption. Okay, so that is that is your interpretation of the Euler equation. Okay, now this has other implications also, and the intuition of this we are going to discuss in the next lecture. Okay, so up until this point, if you have a query, you can ask me.